Hi, everyone. My name is Zhenhua, and this is Zhenhua Wang. Both of us are with Huawei's Big Data Platform team. Today, we are going to talk about course-based optimizer framework for Spark SQL. This is a brief overview of our talk. We will briefly talk about Spark SQL's query compilers, catalyst architecture, and how it utilizes rules to optimize a query. And then we will talk about how we collect statistics. And then based on the statistics, we can estimate the cardinality of each database execution operator. And then next, we will show you, how we utilize statistics and the cardinality information to optimize the query execution plan based on cost. And then we will show you the enhancement we have done with the explain statement. We will summarize our performance results and also show you and also briefly discuss the future work we are going to do. This is a high-level architecture of Spark SQL or query compilers catalyst architecture. A user can submit SQL query or a data frame API. And then Spark SQL's optimizer will generate a path tree. And at this point, it is an unresolved logical plan tree. Then analyzer will kick in using the catalog information so that we know, what variables are the table names and what variables are the column names. And then so it will transform into the logical plan tree. And then the logical query optimization kicks in. So it will transform into the optimized logical plan. And then there's a physical query optimization will come in so that it will enumerate multiple physical plan. And then based on the cost, we will try to choose the lowest cost query execution plan. Then we pass this to the Spark SQL's execution engine. Okay. As you know, Spark SQL optimizer basically is a rule-based or optimizer. It has all kinds of heuristics rules. For example, there's a push-down predicate. It tries to push down the predicate expression close to the table relation node as much as possible. And the column pruning basically means that we want to prune out those columns which are not referenced in a user query. And then also there's a constant folding. As of today, Spark SQL's rule-based optimizer does not consider the cost of each execution operator. Also, say for example, when we try to perform join, even before join, there's some filtering condition. Today, we do the Spark SQL optimizer does not consider the filter factor. As for the join order in a multi-way join query, the order is mainly decided by a table's position in the SQL query. As for the SQL algorithm, it is selected based on some simple system assumption. Then about 2 years ago, I and the 3 other engineers, at that time we were with Huawei's research department. Then we prototype course-based optimizer with Spark SQL. Our work was based on Spark 1.2. After we had a successful prototype, we share our algorithm and the technology with Zhenhua Wang and Fei Wang. They are with Huawei's product development team. So later, they deliver a course-based optimizer in Huawei's product called DataSite. And then in last year's Spark Summit conference, we delivered a talk enhancing Spark SQL optimizer with reliable statistics. And this talk was well received by the community. So later, Databricks contacted us and invited us to contribute our work to the community. So in the past 4 or 5 months, we have been contributing Huawei's existing CBO code to the community. Okay, so today, you can find quite a few lines of code in the master branch. And it is a good and a working CBO framework to start with. And we have been focusing on how to collect statistics. And then based on statistics, then we estimate the cardinality of each execution operator. And then based on that, we help decide, for the hash join, which site should be the build site. And also, on a cluster machine, we also help decide, whether or not we can broadcast one site. And also for the multi-way join query, we try to reorder the join operation. And we have been using the heuristic formula for the cost function. Now I'm going to talk about what kind of statistics we collect. There are two levels. One is at the table level statistics. One is a column level statistics. Okay, and we basically calculate the cost of each execution operator. Okay, in terms of number of rows, generated by each operator, and also the size of output in terms of byte for each operator. And then based on some cost calculation, then we try to adjust query execution plan. And we try to pick up the query plan with the lowest cost. How do we collect table level statistics? We have supported this command, analyze table, and then followed by table name, and then compute statistics. Analyze table, compute statistics, all are the keywords. It basically collects table level statistics such as number of records and also the table size in terms of bytes. We save the information into metastore. And then we use this command, analyze table name, compute statistics, and then we add this clause for columns, and then you can specify the column names. Okay, and by doing so, we can collect a column level statistics. Usually, there's no need to collect statistics for every column of a table. We only need to collect statistics for those columns referenced in the predicate, in the where clause, and the columns referenced in the join condition, and also columns referenced in the group by clause. And for the column level statistics we collect are the distinct count, or basically it means the number of a distinct value, okay, for a given column. And then maximum value, mean value, and the number of nulls value, and also the length for a given type, okay. And this is for the numeric data type, such as integer, double, float, and the date, and the timestamp. You also collect information for the string and the binary type column. For this kind of for string and the binary, we collect the number of distinct value, log, and also the number of null value. Also, for the string column, sometimes you have a short string field. Sometimes you have a long string. Okay, so for the string column, we also collect, the averaging length for the column, and also the maximum length, for the column. There are several database execution operators. Here, I'm going to share with you, two most complex operators. We try to produce its cardinality. The first one is filter. Okay, for the filter cardinality, we can evaluate a compound logical expression. A compound logical expression is connected by the AND logical operator or and the NOT operator. As for the each logical expression, there's usually there's a binary comparison operator, such as equal, less than, greater than, etc. Okay, and for the non-equal operators, we support those columns, of integer, double, and float, and the date and the timestamp, etc. And for the equality, condition, we support the string. I mean, in addition to those numeric data types, date and the timestamp, we also support for the string column. Then for condition A less than or equal to B, A here, I mean integer column, because from the meta store we can collect. We know column A is the minimum value, maximum value, and the number of distinct value, and etc. So when we evaluate its condition relative to B, okay, after we evaluate that, we need to adjust its statistic information. What do I mean? Let me show you an example here. Here, suppose we have a column A, and then there's an operator, then there's a constant literal B, okay? Depending on where this value B is located, because for the column A, we know its range, its minimum value, and also its maximum value. If the value B is less than the column A's minimum value, then for the condition, okay, column A less than value B, then we know that none of the record can meet the condition. So the filtering factor is 0%, okay? And then if B is located within the range, okay, between the A's minimum value and the A's maximum value, then we use, without a histogram, then we use proration, okay, to compute its filtering factor. So here we have the formula B value minus A's minimum divided the A's maximum value minus A's minimum value, okay? And also we need to adjust A's max because the condition is column A less than B, okay? We adjust A's maximum value to B value. If B value is greater than the A's maximum value, okay, then for this case, we know that all the records can meet this condition. So the filtering factor is 100%, okay. Then there's another case, that's both of them are column A and then less than column B, okay. For this case, then if entire column A's range is less than column B's range, then its filtering factor is 100%, okay? If column B's, entire column B's range is less than column A, then to meet this condition, column A less than column B, then we know that none of the record meets the condition. Then the filtering factor is 0%. But if column A and column B, they have some overlap, then we use this empirical result. Basically, it's 1/3, okay, 33.3%. And we got this idea from the book, Database System, and the complete book written by Jeffrey Woolman. Then the second operator I want to share with you is join cardinality, okay. So first we focus on inner join. To do the inner join, A inner join with B on the condition, okay, on the condition A dot K1 is equal to B dot K1. And the inner join cardinality is estimated by what? By this formula, number of records in A times number of records in B, okay? And then divided by the larger value of the number of distinct value in A and the number of distinct value in B. Okay, you can think about, usually in the real world, you have a primary key, foreign key join. And we want to take the number of distinct value from the primary key relation, because the primary key relation has more number, has a greater number of distinct value. Okay. As for the left outer join, okay, then left outer join cardinality is a larger value of the inner join cardinality and the number of records in table A. This is because for the left outer join, A join B, if a record in table A does not produce join record, we still need to include that record from table A. As for the corresponding columns in table B, then we just put null value. Similarly, we do that with the right outer join cardinality. Okay, it is a larger value of the inner join cardinality and the number of records in table B. As for the full outer join, it is the left outer join cardinality plus right outer join cardinality. Then we minus the inner join cardinality. The reason we need to deduct inner join cardinality is because in the left outer join and the right outer join cardinality, they both already include the inner join cardinality. So we don't want to include this twice. Okay. As for the other operators, they are kind of straightforward. Okay. For example, like a project operator, it does not change the row count. As for the aggregate group by operator, we consider the uniqueness of a group by column. If all the columns in the group by clause are not correlated, then we just multiply their cardinalities together. If we figure out, one group by column is unique, then we do not multiply those non-key columns. Okay, then this way can give us better cardinality. Okay, so at this point, I have talked about how we collect statistics and how we get cardinality, okay, for each operator. And then now, Zhenhua is going to talk about how we utilize this information, okay, and then how we enumerate the different physical plan, and then we can choose the lowest cost query plan. So here you go, Zhenhua. Okay.
Okay, thanks, Ron. Hi, my name is Wang Zhenhua. I'm with Huawei's Russell department in Hangzhou. Next, I'll start with some cost-based optimization we did in Spark SQL. As we mentioned before, in the catalyst during physical planning, Spark SQL has many possible physical plans, and the goal of the cost-based optimization is to choose the best physical plan among those candidates based on their costs. For example, for a two-way hash join, we need to choose one operand as build side and the other as the probe side. In Spark SQL, the decision is called build right or build left. At first, we calculate the cost of left and right sides in this hash join. The cost is normalized, and it's a linear combination of normalized rows and normalized size. We use empirical weights in the equation, 70% and 30%. After we get the cost, we can choose the lower cost child as the build side of hash join. Previously in Spark, build side was selected based on original table sizes. Here, let's look at a simple example. Suppose we have a join of two tables, T1 and T2, and T1 has a filter on it. The original table T1 has 5 billion records and 500 gigabytes of size, and T2 say has 100 million records and 20 gigabytes. Because in previous in Spark, we cannot know the filter factor of the filter operation, so the size of the left side is the same of the original table size of T1. So the size of the left side in this case is larger than the right side. So we will choose build right. But now with CBO, we can know we can estimate the cost of various operations like filter. In this case, for example, we know that after the filter, we have 1 million records satisfying the filter condition, and the size is 100 megabytes. Then in this case, the size of the left side is actually less than the right side, so we should choose build left, and this will lead to more efficient execution for this hash join. Besides build side selection, we also there are many other decisions need to make among those candidate physical plans. For example, in Spark SQL, for hash join, we have 2 implementations. One is broadcast hash join, and the other is shuffled hash join. As we know, the shuffle operation in distributed system is very costly. So we are better to avoid shuffle and use the broadcast hash join if possible. In Spark, we have a broadcast criterion, which is that whether one side of the join size output size is small. If it's small enough, we can broadcast that side and use broadcast hash join. Otherwise, we have to use shuffled hash join. Let's look at another simple example. Again, we have a join of 2 tables, T1 and T2, and T1 has a filter on it. Without CBO, since we cannot know the filter factor, the size of both sides is very large and is not under the broadcast threshold, which is defaultly set as 10 megabytes. So we cannot broadcast both either side. So the join algorithm should be shuffled hash join. But with CBO, we can know the number of records satisfying the filter condition. Say, for example, we know that after the filter operator, there are only 1,000 records, and the size is only 100 kilobytes. So we should really broadcast the left side and use the broadcast hash join to execute this join. And we can list many such scenarios. For example, the one side of the join is an aggregate, or one side of the join is another join from other tables. In these cases, we can get a better broadcast decision because now we can estimate the cardinality for different operators much more accurately based on the statistics we collect. Next, I want to talk about MultiJoin Reorder. Currently, Spark SQL's join order is not decided by the cost of candidate join orders. In our algorithm, we decide the join order based on the based on the total cost of the intermediate tables. The algorithm is a combination of heuristics and dynamic programming. And we also use statistics to derive if a join attribute is unique. Because now we have collected distinct count for a column and the table size and the row count of its table. Then we can infer that if a column is a primary key when its distinct count equals row count. And this information is very, very useful and can benefit star join queries because in many real-world scenarios, joins are often performed between primary keys and foreign keys. So if we can put this kind of joins in front or at the bottom, then we have a good chance to reduce significantly the intermediate output. In terms of cost model in the algorithm, we also can take shuffle cost into consideration. So far, this join reorder algorithm is still under development. In order to better understand player selection and inspect the statistics in each operator, we also enhance the explain statement so that it can display statistics for each operator. Statistics include size in bytes, row count, and broadcast hint. In the following example, we can see that in the optimized logical plan, in each node we have some readable information about its statistics. For example, for the project node, we know that its output size is more than 300 bytes, and it has only 8 rows. Next, I want to show some preliminary performance test results. We generated a TBC-DS dataset with scale factor 2000, which means the size is 2 terabytes. The tests are run on a 4-node cluster, each with 40 cores and 380 gigabytes memories in each node. And we use the latest Spark development code. The TBC-DS dataset has a total of 24 tables and 425 columns. In the statistics collection test, it takes 24 minutes to collect statistics for all tables and all columns. And that's pretty fast. The reason is that all the statistics we collect are computed by integrating with Spark's built-in aggregate functions. And it should take much less time if we collect statistics only for those columns used in predicate expression, join, and group by. And here I want to share with you some query performance results with broadcast decision. We run a subset of queries and list some queries with good performance improvement. And we also list the query response time with or without CBO. From the results, we can see that good broadcast decision can bring us 10% to 6 times speed up. As we are still developing and contributing to Spark, we will share with you more information and more results in the future. Okay, about the current status, we have an umbrella JIRA of this CBO work, which is Spark 16026. So far, we have created a total of 24 subtasks. 17 of them have been resolved or closed. 5 of them are coded and under review currently, and 2 subtasks are still under development. And so far, more than 5,000 lines of Scala code have been submitted. These codes went through rigorous code review and lots of rewriting. But good quality comes out after the review and the rewriting process. And we expect the first version of Spark, the first phase of Spark CBO, to go in Spark 2.2. In the future, we want to support some advanced statistics in order to improve the accuracy of cardinality estimation. For example, histograms, sketches, etc. And we also want to support partition-level statistics for partitioned tables. Other future work include a detailed cost formula for physical operators and a more efficient statistic collection method by sampling data for large tables. Okay, that's all. Thank you.
We've got about 1 minute and 15 seconds. I know it's between you and lunch, so we've got 2 speakers on either side. We can take maybe one question if you want. John.
Can I go ahead? Ask
yeah, go ahead.
So at what point does the stats get built for a query, and how long does it retain? Can a query leverage that same stats over and over again? And one more part to that question is, did we not look at the indexes as in traditional RDBMS to do some of this at all, like clustered, non-clustered in a SQL world?
Okay, first question is, hello? The first question is, the first answer for the question is, we collect the statistics when user type the command. And if the in current stage, if the statistics get old, the user it's the user who should be responsible for rerun the collect command.
Okay.
It's not an auto update feature.
No.
Like stats doesn't get updated as the data changes. Okay.
Yeah.
Yeah.
As for I think the second question is regarding index, right? I think as of today, Spark SQL does not really support index. But with the statistic information, we can derive whether or not a column is unique. And based on this information, it can help us find the accurate plan. For example, if we know that's a primary key, then we can better estimate, say, how much the size of a hash table. Usually we use hash table to do the hash join, and we use hash table to do group by. Okay, so if we can estimate the size we need for the hash table, then we can avoid this out of memory error. Yeah.
Thank you.
I think we don't have any time for any more questions because it's lunch waiting for you guys, but I'm sure you can probably ask him offline here. Thank you. Be welcome to John and Zhenhua.